international group. So that's how they coordinate the schedules in advance, and then once it's loaded into the software, that it's automated from this point.
Cool.
Okay. We have people who are taking pictures along the way.
Well, there's still a little bit of light to get some pictures.
So we have Stephen Merkowitz is the Space Geodesy project manager. So these instruments and the NASA Space Geodesy effort is under his management, and so I will hand it over to you, Stephen.
All right. So you guys are just coming from the MOBE 7?
We did the MOBE 7 itself, not the ILRS.
Okay. Good. All right. Well, welcome. You've seen the main attraction here, which is our VLBI antenna. So this is a radio antenna that works with a global network of other antennas that they're observing the same sources at the same time, actually distant quasars. And the purpose of this is to monitor the Earth's rotation and orientation in space. We do sessions throughout the week. Today it's not being done continuously. We don't need to do that yet, but the move towards the future is to do continuously. This is the next generation system. The current systems are much bigger antennas, bigger, slower, more expensive, but they're the ones that do the workhorse of today. But this is what we're moving towards, and you can see it's a much faster antenna. It moves fairly quickly from source to source. You'll also hear about the data recording speed, which is about a gigabit or more per second. So it records much faster data, and it's also a broadband, so it sees much more of the radio spectrum. NASA, we have this prototype system here, and we just finished a new system in Hawaii that's 2 to 4 times as fast as this one. It sits right next to our Legacy 20 meter on the island of Kauai. We have a Legacy station in Brazil as well, but we cooperate with a global effort, which is about 40 some odd stations. Some of the stuff that this is used for, it's used to create the daily Earth orientation products that are used in order to make GPS work, so you can figure out where you are on your phone. It's used for satellite navigation, Earth observations, as well as you combine it with other techniques, precision farming, surveying, a whole variety of applications. So we, as the Space Geodesy program, are all about position, navigation, timing. It's the study of the Earth's shape, orientation, and gravity. So we cover the full dynamics. John might be able to give you a little bit more of the history, but as you walk around and see on the other side of this, there's a 5 meter antenna, which is the Legacy old days, the mobile VLBI system. So back in the days before GPS, we used to mount these things on trucks, and these are some of the original trailers from them, and they would drive around to interesting spots all over the world to measure the crustal motion. And so VLBI was the first technique to actually measure plate tectonics. So before that, people just said, well, the continents are probably moving, but after VLBI, we knew they were. Today, GPS is a much better technique for monitoring it. And you can actually see across the site several GPS antennas. We have one right there that kind of looks like R2-D2 sitting on the ground, and if you look in the fields on your way back, you'll see these mushroom-looking things that are also fancy GPS antennas. I don't know, John, if you want to say anything?
Sure. So Steve was talking about these antennas measuring the Earth orientation, or the orientation of the Earth in space. And so I just want to say a few words about that. We grow up learning that the Earth rotates once every 24 hours around its axis. That's sort of true, but what happens is the rate of rotation varies over time, and the position of the North Pole varies over time. So the position of the North Pole wanders in a circle about the size of a baseball diamond with a period of about 430 days. And the rate of rotation of the Earth varies, has seasonal effects. So in the Northern Hemisphere winter, the days are about a millisecond longer than in the summertime because you have angular momentum going into the atmosphere. So we need to measure this so that when you have your GPS positions, you could correct for that. If you didn't correct for the rotation of the Earth, your GPS positions would be wrong.
You guys probably also remember to reset your clocks back in January, right? By a second, there was a leap second introduced. All right, the leap second is introduced because there's a difference between Earth rotation and clock time. Clock time now is being kept by atomic clocks, and they get out of sync. And so, precisely for the reasons John was saying of the variations, and it's somewhat predictable, but not completely predictable. There's a variation in it. So the Earth is slowing down, but it slows down by varying amounts. So the frequency by which you introduce a leap second changes over time.
As Steve was saying, the rate of rotation of the Earth has slowed down, and it's slowed down since constantly. When dinosaurs were around, one Earth day was about 20 hours. And eventually, it's going to slow down until the Earth and the Moon are locked in step with each other. So it'll be about 30 days. So the precision of the measurements is very precise. You know about angular measurements. So if you held up the postage stamp in San Francisco and you looked at it from here, the angle it subtends is about how precise our measurements are. So, you know, the most precise measurements we have of this.
So now we probably want to maybe split up the group. Larry Hilliard over here, he's one of our engineers, is going to take some of you inside so you can see the electronics racks. You can see the the 1950s technology along with the this millennia technology right side by side, and the others we can continue to take pictures or chatting.
Cool. Take this side of the group that's a little bit closer to this perhaps. This is the legacy antenna that used to, back when we were proving the crustal dynamics and the plate tectonic theory, these were on the back of trailers. And then this trailer went along for the ride, and what they do is they have the front end sort of analog electronics up in the antenna, and then they digitize it. And I'm gonna take advantage of the fact that the slideshow here is at the beginning. This is something we put together for Maryland Day, just an opportunity for public outreach that we had a couple of years ago. And it sort of shows in cartoons the quasar energy coming down this phase front, washing across the Earth in two different places, forming a baseline. And then it's very important that we have a precise tick going that doesn't change from here to Massachusetts to Hawaii to wherever our antennas are collecting it. And that tick is created with a hydrogen maser. So we're using the hydrogen atom as our tick. And then we connect with GPS to the constellation to get that tick, everybody on the same page. So you have a 1 PPS, I guess, absolute, this is the second, and then the relative tick or whatever is kept with the maser. And then that 1 PPS is sent all around the system so that as you collect the data, as you collect it in the antenna, you filter it down, you put it back together here, you digitize it in certain selected bandwidths that don't have as much radio frequency interference in them, and you get the best data that you can into 4 1 gigabit slices, and then you channelize it further, and it's a real big accounting task before you correlate. But if you've engineered it right, then it sort of automatically happens because you've distributed that 5 megahertz from the maser all around the system, the 1 PPS that you're comparing to the GPS 1 PPS from everywhere else. And so what this slideshow did for Maryland Day is it actually did sort of a time-lapse photography. Now there's a quasar that all these stations are looking at, and so IVS, for online media or whatever media day, you can check the IVS live,
And so whenever we have a session, like the legacy sessions go Tuesdays and Thursdays, we're doing with the legacy network, and then every 2 weeks with our R&D, with our newer systems, we're running a session as well. And so the hope is that we'll be able to do all this from a central place. Now what this is actual real time, and this is a system that's measuring the cryogenics. Now this, it's zoomed way in so it doesn't look as flat as it actually is, but this is a 20 Kelvin temperature that's being maintained at the most sensitive of the electronics, that very first amplifier and the feed horn that's up looking at the subreflector in that antenna. And then sort of the envelope cryogenics at 70 Kelvin, liquid nitrogen temperatures approximately, is around it. So you've got two thermal zones there. You've got your ambient temperature, you've got your 70K range, and then you've got your 20K range where you actually have your sensitive electronics. And then the other graphs here are showing the pressure, which is necessary because we actually do it with a compressor and not liquid nitrogen or liquid helium, but gaseous helium, and then pressurize it down. This is the core brain of the VLBI, and it's called the field system. And some version of the field system is that all the antennas are all around the world. So
So Larry, we're going to swap out these.
yeah,
mini
that's
groups.
cool.
Thank you.
Thank you. Thank you.